Our first talk is by Vanden-Eijnden from the Courant Institute, and he will be talking about non-equilibrium transport samplers. Eric.
Okay. Good morning. Thank you everyone for coming. Thank you, the organizer, for the invitation. It's a pleasure to be here. Always a pleasure to come back to Cambridge. So what I'll do is I will discuss a class of non-equilibrium samplers. This is joint work with Michael Albergo. It was great that Christoph gave his talk yesterday, because I'm going to be able to build quite a lot on some of the things that he already introduced. And if there's two take-home message that I'd like you to come on with after this talk is one is that thinking continuously in time can be useful, like Christoph already said. And second, that if you have not done so already, you should start to look into the tool and concept of machine learning. Okay, and I'll try to explain this. Okay, so I will describe to you using old-fashioned. Let's take annealed importance sampling, which was introduced by Neil, but the version that I'm going to be mostly discussing here is a time-continuous version. We can always discretize everything without bias at the end, but as I say, it's easier to think time-continuous. So the idea will be like this, and this really fits what Christoph was discussing yesterday, is that we're going to pick a time-dependent potential, which we assume bounded below, and such that we can associate PDF to it, right? And that we define in such a way that at time t equals 0, we can associate with it a Gibbs density that is easy to sample. And at time t equal 1, it gives the target density that we are interested in sampling. Okay, so this could, for example, be something which is non-convex, so that this is a multimodal PDF, and this could, for example, be a Gaussian. I'll give you an example of it. Right, so that's the first step. And then the second step is that we will generate sample from this base, which is easy, and then we're going to evolve them in time so that their law tracks the time-dependent PDF at all times, the one that is associated with the time-evolving potential, in such a way that eventually they should end up on the target. Okay? And so this is not ergodic sampling. This is really a non-equilibrium sampling strategy with dynamical transport of measure on t equals 0, 1, from rho 0 to rho 1. And of course, the question is, how can this be done? And this was already explained, in part by Christoph. But I want to make a point that, that is maybe obvious to all of you, but, might be worthwhile emphasizing again, is that this time-dependent PDF, which is associated with a time-dependent potential, is not the law of the solution of this SDE, the Langevin equation. Okay? And the reason is that this SDE would allow for ergodic sampling on a frozen potential, but this potential is moving. And so, the worker can lag behind, colloquially, what the time-dependent potential does, and that introduces a bias. There's a little movie that illustrates maybe, both the procedure and the bias, which is, this is what happened with workers following this evolution in a potential that goes from a Gaussian to a mixture of Gaussian. Okay? And maybe the bias is not so apparent here, but what happens is that the way the workers go into this mode or this mode is basically fixed by the initial condition on the base distribution, and so there is a bias. It's not the right weight on the two modes. Okay? It's not, the movie doesn't show what is the actual, empirical density, but it's not the target exactly. Okay. So the observation of Niels and Jarzynski is that you can actually correct that by adding dynamical weights. Okay, and that's also what you do in sequential Monte Carlo. And so the little theorem is written here is that you take the same equation as before, but as you simulate this guy or evolve this, you also evolve a variable scale, a variable a, okay, that evolves in the time derivative of ut, evaluated along x. And then what you can show is that if you don't take expectation over this, which has a bias, but you reweight using these exponential weights, then you can calculate expectation exactly. Okay, and you notice that I forgot to mention that in this expression, you only need to know ut, which means that you need to know all of these PDFs up to a normalization factor. And in fact, this formula allows you to calculate this normalization factor, or at least its ratio with respect to the normalization factor of the base that you may assume you know if it's a Gaussian. And in fact, in the physics literature, this is what's called Jarzynski equality, which is this expression for the free energy, which is minus the log of the partition function, which can be expressed in this way. And as I already said, this is a time-continuous version of IAS, and you could potentially not do this, but use the weight for resampling, and then it would give you sequential Monte Carlo. Okay? Okay, I'm going to give you a proof of this, just to emphasize the point that it's actually easy to think in continuous time. The proof is elementary, is actually based simply on the fact that we know what this density is. We know its explicit form. So if you take its time derivative, you know what it is. This is just because you know what rho is. And then in this expression, you can always add this term, this additional term, because it's also equal to 0, since rho t is that, so it's in local detail balance with this. Okay. Then you realize that you can, if you extend the state space and you write, so the problem with this equation that there is a term here which is not a transport term, but you can extend the state space, add a transport term now in this scalar variable a, and then this step I'll let you do as a little exercise. You can show that if f satisfies this equation, then rho defined in this way satisfies this equation, and since the solution of all these equations is unique, that means that gives you the identity. And then that means that if you take expectation with respect to rho, well, you can use that to re-express it like this, and then remembering that, no, this is a transport equation, right? It's a Fokker-Planck equation. You can know, what is the SD associated with that is the one I wrote in the theorem before, and so you can re-express this expectation simply like that. And that's it.
And you're not supposing that at time t you are in equilibrium at that potential ut?
No, if you were in equilibrium, then you would not need the weights. All here is happening on time t equals 0, 1. There is really no equilibrium sampling, okay? Like in Niels' important sampling. Okay, so you may say, well, is the problem solved? Well, no, because unfortunately, the weights can have bad variance. And the reason why you can immediately see why that might be the case is that, in fact, in this procedure, you don't change at all the way the walkers are moved. The only thing that you do is that you equip them with weights. Okay? So let me give you another little movie that illustrates maybe the difficulty. This is a target 40-mode Gaussian GMM, so Gaussian mixture model, with samples as they should be on it. Okay? And this movie shows you what happens if you take a potential that goes from a quadratic, so a Gaussian, to this mixture. And what you see is that the walkers are lagging behind, exactly because intentionally here the potential is moved a little bit too fast, right? And so the walkers that you have in the theorem before, or in general in IAS and in important sampling, are these guys. And you see that it would be completely hopeless to try to reweight that towards this, because there is simply no samples where they should be. So the weights are, the variance of the weight is catastrophic here. Okay, so that's why in general the method fails. Okay, the bare method. Yeah.
Are you considering now with the potential at type t to be a linear interpolation between?
In this one I did that. Yes, okay. Yes. For this, we can do other choices. For the moment, it's just yeah. Okay, so the obvious question is, can we fix this issue by adding some transport? Okay, and well, you can, again, same little manipulation. Suppose that I add a transport term. So this again, I'm looking at the evolution equation for the PDF. Remember that this is evolution equation. Again, I know what the PDF is. So these are all manipulations that are essentially involving zeros. Okay. So you can add this term at the left-hand side and compensate by this term, the one in red, at the right-hand side. Because this is equal to this, again, because we know the form of rho. Okay? And then, as before, we can always add this term as well, because this is also 0. Okay? And so if we write this equation, you see that what has changed is that there is an additional transport term, and as a result, we have modified this term, which govern the dynamics of the weights. Okay, well, that means that we can proceed exactly. I'm not going to repeat the proof, but you can just write down a set of SDEs where instead of having this ULA with a time-dependent potential, we have added a drift, and we compensate here by making that the weights have an additional term, and the statement remains the same. In fact, this procedure is fairly old. It was proposed originally by Jarzynski and Van Kootenatan in 2008. Okay? Notice that there's a remarkable fact here, is that this doesn't need to be a gradient field. So this doesn't even need to satisfy local detail balance, meaning at every fixed time, right? This B can be anything. Okay? And well, okay, so then what's the next question? Is that, okay, so first of all, before I say that, this is the place where I'm not going to show it, but you can time discretize everything here, right? By doing it, for example, you can time discretize this to turn it into ULA, and then you can modify this thing, this rule, in such a way that the weight now will correct not only from the bias that is coming from the lag because the potential is moving, but also from the bias from the ULA step. So you can do exactly what's done in IS. I'm not going to show you the formula, but it's fairly elementary. Now we have an additional knob we can play with. That's B. Okay? And clearly, what you may want to do now is to say, well, let's try to reduce the variance of the weights. Okay? Which is, let's try to use this guy in such a way that it moves the walkers now in a way which is better, so that they track better the time-dependent potential that we have. Okay, so, well, observe that if this, which is equal to this again using the form, these two guys, the first equality is simply because we know rho. But suppose that we impose this, that this is equal to 0. Okay? Well, that would essentially mean that the weight that were in the equation before would be equal to 0, and the transport alone would transport, so the drift alone here would transport the PDF, the target PDF rho t. Okay? And as usual, if this is true, we can also add this term, right? Because this term doesn't change anything. So what we have here is that this equation, if this equation is satisfied, leads to perfect transport for any epsilon, including if you have no diffusion coefficient. In the original IAS, you can also take no diffusion coefficient, but then it becomes a little bit trivial, because if there is no diffusion coefficient, the walker don't move, and it's the weight that needs to do all the work. This is the extreme case where reweighting become really bad. Okay, and this is the ultimate one where you don't need the weights at all because you have modified the transport. So how do you do? Can you turn this into something which is actionable? Well, the answer is yes, because you can write the. So you need to think about this as an equation for B with rho given. Okay, and so you can write down a variational principle for this. It's written here, which is, it's called the pin loss because it's called a physics-informed neural network for a reason I'm going to explain in a minute, where you just take that, you square it, and then you take its expectation with any PDF. Okay. Eventually, we will take that this PDF is that guy, but for the moment, notice that if the minimizer of this objective is 0 if and only if this guy is equal to 0. Okay, so you solve the equation she's taking. And so if you do this, so if you can show that the minimizer of this, right, any minimizer of this is such that the minimizer gives perfect transport, so this is satisfied. Ft is the free energy. Notice that we don't know F, but you can actually include it in the objective and just, it's a Lagrange multiplier for the normalizations. You can learn it as well if you do this. And on this, any one of these minimizer, you have that the loss is equal to 0. Okay. So now, I mean, you'll have to bear with me for a little bit. I'll come back to this at the end of the talk. This is the part where, you may want to say, okay, well, that's fine, but, how will you ever solve this minimization problem if you have in any situation of interest where you could have that this is living in a high dimensional space, okay? But this is the place where you can use machine learning. And you need to bear with me for a little bit. I'm just going to tell you what you need to do, and then at the end of the talk, I'll elaborate a little bit on that. But the basic knob of machine learning is to say, use a deep neural network to approximate these functions. Okay, there should be a hat on these. Okay, then evaluate the objective empirically using samples from this distribution, which could be, in fact, the sample from the procedure. And then do the minimization using all the toolbox of the machine learning. If you have never played with that, what I just explained will be very obscure, but if you know what machine learning does, it should be fairly clear, and I will explain more about this at the end of the talk. Okay? This machine learning gives you a way to actually find approximation for this function, even in high dimension. And I'll elaborate on that at the end of the talk, I promise.
Where high means? Where high means?
In the example that I'll show you, it's millions of dimensions. Okay, notice that if you put rho hat as rho t, which is the target, well, you can actually write this expectation like this using the weights, right? And what you recognize here is, in fact, dTA, right? So what you see is that essentially what this, this loss, if you put it on policy, which is that if you use that, right, is a way that really controls the variance of the weights, because you're trying to minimize this difference here. And at the minimizer, what you have is that dTA equals dTF. Okay? And so that means that in that case, when you get this, this is the expression that you get. That means that you don't need the reweighting is deterministic, which is, again, what you needed to have. Okay. So here's a little movie that explains that. This is the 40 mode GMM. This is what happened. So this is no transport, the original AAS. This is what happened if you put transport. Okay? And this transport has been learned with the way I'm going to explain it later. And as you can see, the potential move in the same way in both. It's again linear. But the worker here are tracking what this potential does much, much better. Right? And you can actually, you can play with the knob that you have, which is with the epsilon, and by, putting a little bit more, so this is, what I'm explaining here can be done with any value of the diffusion coefficient. Typically, if you were to take the diffusion coefficient to infinity, right, in IAS, eventually you'd get that the weights have zero variance. But typically, this limit is not achievable because the transport is, it would be too bad to, you can't do it. But with the transport added, it's more easy to actually reach very good ESS, like written here. Okay? Maybe one more theoretical result, and I'm going to put two examples. The objective control the KL. So you can show that, suppose that you transport a PDF with the wrong B. And then you ask, if you use the wrong B, and you don't, epsilon equals 0, not only this transport, then you can ask what is the KL divergence of the PDF you will reach at time 1 with respect to the target. And this is dominated by the value of the loss. Okay, so the loss gives you really control the error. Okay, let me flash by you two examples. Actually going fairly fast, so all good. So this is 8 mode GMM in 36, 64, 128, and 200. I don't know why we didn't do 256, but that's Michael decided these numbers. So you see slices here, right, of this. This is the target, and that's what the model does. And what this graph does here, we could do other thing, is that it shows what happens if you do IAS without transport and increase the diffusion coefficient. And what happens if you learn the transport and increase the diffusion coefficient, and all of these curves are for the dimensionality as it increases. And what you see is that if you increase the diffusion coefficient in IAS, right? Remember that if you increase diffusion coefficient, it comes at a cost because it means that the discretization step needs to be smaller. In IAS, that would mean that you need to take more steps. Okay? If you do that, right, the cost increases. And you see that the improvement in effective sample size are not significant. In fact, especially if you go to in 200 dimension, nothing happened, even though you have taken a diffusion coefficient which is fairly high now, and you need to take a very small time step. But you see that with transport, okay, so you see that you can maintain reasonable AS at even without diffusion coefficient, and if you increase it, it actually reach values that are close to 1 fairly quickly. Okay, so it's you know you see that you can reach this kind of epsilon to infinity limit much better with the transport.
The ESS here is just defining based on the variance of the
weight. Yeah, exactly. It's the variance of the weight. Yes. I mean, there's for example like this, there are other things that we could compute, but that's the easiest one. Okay, and you know I know that the ESS is a measure that is quite dangerous, but in an example like this, you can overkill it. Yeah.
Do you know anything about what is the optimal B for these simple models? Too hard to get any kind of law?
No, I don't know. I mean, it actually is. I mean, the difficulty is that you need to solve the equation that you wrote is essentially a Poisson equation. So you can solve it for linear U. Okay. So if you move a Gaussian, if you take this formula I written in the paper. So if what you have is you have a Gaussian where you move its variance, covariance matrix, and mean, then you can find what the B is, okay? And in fact, it's pretty nice in that case. It's just kind of, you know, it can be a linear drift. This is what it is. And this example is also not completely trivial because even if you move a Gaussian in high dimension, IS typically fails. Right? It's kind of a, you know, dimensionality is really tough. Okay, here's another example. Okay, is the 5-4 model. You can think about this as a continuous version of an Ising model, in which you know the spin are not plus or minus 1, and they're not on the sphere; they're on R, right? And they're on the grid, and then you just put the you know so they have an exchange term, which is the equivalent of the summation over nearest neighbors, and then there is a you know a quartic term here. And so what happens is that if you change, okay, so these are notation from high energy physicists. So m squared here can be negative. So what happens is that if this term is sufficiently negative, this is a double well, and so you can have phase transition. It's actually difficult to to sample past the phase transition. And what you see is again that if in example like this, which become non-trivial in terms of dimensionality again, because the number I don't know how many spins there is, but the dimensionality is this, the number here and the number of there. But I don't remember what it is, maybe 400. You see that this is no log scale. That the transport allows you to maintain the ESS, whereas without transport you can't do it. This axis that has disappeared for some reason is in fact in time. That's the ESS along the transported field. Okay, and it shows that you can, in this case, for example, you go past phase transition. You see these samples are mostly +1 or -1, right? This when m becomes negative. You see that you go past phase transition, where the ESS without transport completely drops, but you can maintain it at fairly high value. This is a log scale. Right? Okay. Okay, so I still have a little bit of time. And so we are working on other examples, but I didn't want to flash that by you because what I wanted to discuss now is a little bit this idea that what I've explained here is that if you do sampling and then you do some learning on top of it, right, using machine learning, you can actually achieve things that otherwise would be very, very difficult. So I want to elaborate on this. And I know that this might be something which is quite new, but I thought it might be interesting to you a little bit. Okay? So, you could ask the following thing, which is, if you want to sample with flow and diffusion, you may ask, suppose that I have a base measure that's simple, and I would like to have I want to sample from a target. So if you generalize the ideas that, put them in the broader context that I just discussed, you might want to say, can I construct an SDE, or in fact an ODE, if sigma is equal to 0, which would be such that if you start with initial conditions from the base, which are easy to generate, and then push them, it's again non-ergodic sampling, push them in time t equal 1, you would get sample from mu1. Okay, and of course we know, from standard result on dynamical transport of probability measure that there are fairly weak conditions on mu0 and mu1 that guarantee existence of a transport like that. The question is how to identify it in practice. Okay, is there anything actionable that can be done there, right? If we were able to do this, well, it would be very easy to do samplings because you would draw a sample from the base, push it through the ODE or the SDE, which can be controlled because we have good discretization scheme for this equation, and you'd get a sample from U1. Okay? And this little image here shows you what that would do. And this is an image that comes actually from simulation within machine learning. So what you have here is that the samples that you have are just images. Imagine that every one of these images, they are pixelized, and so you can vectorize this into this one big vector in RD, a gigantic D, because you have 512 by 512 pixel or 128 by 28, and many channels on every pixel to tell you what is the color, etc. So it's a huge dimensional space, right? And then in this case, what you would do is you say, suppose I give sample, this is the distribution that I would like to sample, right? And the learning would be done. In this case, there's the sampling is actually a bit trivial in this data because you have given the sample. They are the data set. For a distribution you don't know, but what you'd like to do is to get a generator that would give you more images. So I don't know if this actually rings a bell, but it actually, that's why this figure is that there's something that has been done and that you probably have played with, okay? Which is, this is the mechanism between all of these image generators that you can play with in the web, like Stable Diffusion, DALI, etc. These are fake images that are generated simply by entering a prompt. You can guess what the prompt is, sort of, right? How was this done? Well, it was done with a procedure like this, and this was first introduced in this paper that was a breakthrough, where what was learned is really a drift that allowed to move pure noise, like in the movie that you had before, into these images. Okay? And so I'll spend a couple of minutes to explain to you how that is possible to do, right? And we're not describing what these guys have done, but by describing a procedure that we have introduced, okay? So imagine for a minute, so I'm describing another paper with Michael and with Buffy, and there are two other papers that provide, do the same. So imagine for a minute that you have at your disposal sample from the base and sample from the target, okay? Eventually, we will need to incorporate that in an active learning strategy where you will have to, if you do Monte Carlo, we don't have access to this, you need to generate. But for the moment, assume that we have some samples already. This is the case in data science again, because in data science, you will have a bunch of samples that, for example, images of cats, dogs, celebrities, okay? So what you can do with that is that let's introduce this, this stochastic interpolant, which is just a linear interpolation, a little bit like we were doing before with the potential, but now let's do it in sample space. You pick a sample from mu0, you pick a sample from mu1, and then you kind of draw a line between the two. Here, there is no noise, but you could imagine adding a little bit of noise, and so this is what this is giving. I'm pairing a sample here to a sample there, okay? And in that way, you construct a process that goes from there to there, okay? And of course, this process has a probability, has this time-dependent measure associated with it. And if you want to see what this time-dependent measure is, well, you can just look at the cloud of points. This is a cloud of points where we have drawn from this two-moon distribution, the x0, from the checkerboard with this, from mu1, pair them, and this shows you the measure of one goes to the measure of the other.
You pair them randomly?
Yes, you don't. There's many knobs you can do. You can do a pairing here to get optimal transport. This is just random.
It's strange. It doesn't look like in the picture, like you don't see people moving completely, but maybe it's too difficult to.
Well, it's actually difficult to follow, right? But they do, in fact. Okay. Okay. So then there's a little result that you can show, which actually is sort of remote. So this is. Having access to this, right? is not a generative model because you have access to this if you have sample of x0 and x1. What you'd like to do is to get a generative model where I pick an x0 and then I can push that guy into an x1. Okay? But there is this result that is actually fairly simple to prove that says that the law at each time of this guy, this IT, this interval, is the same as the law of the solution of this ODE, provided that the drift that you take here is the conditional expectation of the time derivative of this one. The time derivative is very easy to calculate. It's just x1 minus x0, where you take the conditional expectation at it equal x. And this conditional expectation, if you use the L2 characterization of it, can be written as an optimization problem. And so you can again, sorry, I want to go back. You can estimate this loss using the data, if you have data, right, which is from IT. And then you can again use the toolbox of machine learning to actually try to minimize this. So what I don't have time to explain that to you, but let me kind of in detail. But again, what that mean is that you use a deep neural network to represent B. Okay, that's a parametric representation because this neural network depends on a huge number of parameters. So this turn this loss here into this objective into what in the parlance of machine learning a loss for the parameter in the neural network representing B. And then you can evaluate this loss on sample data. Okay, that gives you what's called the empirical loss. And then you can do gradient descent by taking batches of data. That's called stochastic gradient descent to actually optimize the parameters until convergence where you have the approximation given by the machine learning code for your B. Okay? And now, this...
And you always, you always keep track of the error that you make. You'll find out if the problem is too complicated.
In machine learning, that actually is difficult to do. Okay? So let me elaborate a little bit on this. If I had explained this, or proposed this 10 or 15 years ago, right, it would have sounded like total lunacy, which is to say you're going to make a minimization here to learn a function. This function is a function from RD to RD, where D can be in the millions. Okay, it so turned out that for a reason that remains at this stage a little bit obscure, though there are elements of answer, this turned out that it can be done with machine learning. And here is, if you do, so what you do, what these examples show is something that is with the method that I just described, done on 1 or 2 GPUs. So this is really not the kind of thing that is done at OpenAI or Google. But this is the kind of images that you can get from pure noise. This is a fake tiger. It's not in the data set. Okay? And now I want you to pause a minute to this, and because I am flabbergasted each time I see this, so I'd like to convey that to you. What has been learned here is a velocity field that moves noise on every pixels, okay, and turn them into this. So I know that there's many things that could go wrong here, like overfitting. You might say it is in the data set or things like that. But even if it were, you have learned the velocity field that allow you to do this. That is completely remarkable. Right?
Just to be sure, in your case for your algorithm, it's not a problem if you don't exactly have the optimal P, because you have always... If you
That's
have
right. The optimality here is not about optimal transport. Yes.
Not talking about optimal transport, I mean the minimizer of your loss. If I give you any field BT, your algorithm...
For nets, yes. Here no.
Yeah, here no.
Because here there's no control, because you don't have an oracle that gives you what the density is. You don't know what is the probability of this density, okay? So here are the little tasks that you can do. This is a noisy image that needs to be denoised into this. And so what you have paired is images from here on the training set. This is what happened when you then test it. You take this guy and it kind of gives you the detail. There's too much light in the room, but in fact the details are pretty good. There's another thing that you can do is that these are images where you randomly mask them. So here you see the noise. And then the velocity field that you learn, what it does is that in the places where there are these masks, it actually kind of puts you the image that should be there, even though it has not seen it. Okay, and you can, hold on a second, you can see that it actually does a fairly good job. Right? Okay, so this is, you know, sort of to kind of illustrate through pictures. So I know that this is, you know, there's no theorem here, but this actually, that it is possible to do things even in high dimension and to learn transportation of measure. And that, I think, is a remarkable fact. These advances in generative AI are perhaps the most novel that have happened in AI. Like, you know, many of the things in AI, where the concepts were already there, you know, a long time ago. What came out is the scale, right? Like neural network, etc. But these ideas to do transportation of measure were really something which is fairly new. Okay, to think about it in that way. Okay, and so that brings me to the end of the talk, actually, which is, you know, I'm going to say something which is a little bit provocative. My conclusion is that you know, I think that we should all learn to sample better. By learn, I mean machine learn. Okay, and what I've explained here, I told to you about, you know, in the case of nets, but this is a general strategy, which is that these generative models that they've been used in situations where there was data available can also be used to assist Monte Carlo method. The idea being that you can, you know, transport samples to get better move if you do metropolis hastings, or, as I explained with nets, to get samples that have better weights, important weights. Okay, and there's many papers here, including some by us, that actually are doing, you know, trying to do these things, and you know, there's actually kind of nice mathematics associated with it, except that unfortunately, at some point, you know, you need to work in suspension of disbelief, which is at some point you need to say, and the neural network that I will use will be capable of doing the optimization that I asked it to do. And that is, you know, but as I say, so there's also a beautiful mathematics there, but if you know, you can leave that aside in the assumption if you wish. Okay. This, however, and this is my last point, I want to stress that the advances that I've shown you in generative AI and ML are of a very different nature than the one that, you know, we need to assist Monte Carlo. Why is that? Well, it's because the standard setup of ML is that you have data and no model. Like, you know, what in ML is called sampling is actually a strange thing, because you are given samples to begin with. You're not giving a distribution. You're given samples, you will just generate more samples, right? We typically are interested in another problem where you have a model but no data, the model being the distribution that you know maybe up to a normalization factor. So this is very different, right, than this, and in a way it's harder, obviously. Right? Because, you know, if you don't have data to begin with, it's a bit of a chicken-egg problem where you need to generate the data. Actually, that's the problem you started from. So clearly, it's actually complicated to do, and that's why, you know, the advances into using generative model for Monte Carlo are only beginning. But I believe that they will have a profound impact, simply because you can see from, you know, the image that it's possible to do. Now, you know, there's a bit of a curse into this, but there's a blessing associated with it, which is that when you do generative AI with data, there is essentially no validation possible. At the end of the day, the only thing that you can do is look at the picture and say it's a nice picture. Okay, there are tests like, you know, fresh air inspection distance. There's kind of that are shown in the literature, but as you know, as statistician, you know, these tests are very bizarre, like because essentially there's no ground truth. If you do Monte Carlo, there is ground truth, as was pointed out, right? If you do a generative model, you can always correct with the weights, and you can also inspect the weights, see what is their variance, or, you know, inspect what is, for example, would be the acceptance ratio in your metropolis hastings. So what that means is that there is possibility of validation, okay? And that is something which is extremely valuable to have, and would lead to something that, you know, that people are really talking about a lot, is the instances of verifiable AI. So it would still not be verifiable a priori, in the sense that you would say, oh, if I know that I will be able to solve this problem because I will take this network, you would need to do all the, the calculation. But a posteriori, you could a priori check in this setup whether you have gotten something which is close to the ground truth or not. It's a hit or miss, but you can tell whether you have hit or missed. Okay. All right. So with this, so this is the end of my talk. If there's a few references here. This is a paper that I discussed about the sampling. This is the one about this interpolance. This is another one, and these are if you want to learn a little bit about Monte Carlo sampling. I realized that my talk was a little bit more like overview and conceptual than the other, but I hope you got something from it. Thank you very much.
Very interesting. I mean, let's say this from going from T to 0 to T to 1 is what, let's say, base physicists have tried to solve with simulated annealing, simulated tempering, and all these methods.
Yes, this is a variant of that, right?
And of course, I mean, this is progress on that. We're trying to move on the technology of these methods that are very important. These methods then run into problems when between t equals to 0, t equals 0 and t equals 1, you have a phase transition, or you have a line of phase transition. So what it means is that the model that you doesn't change so much, but the probability distribution jumps in sample space just enormously, and even it jumps at every parameter of t. It jumps so that so how would your model help us if we want to use this?
So, I mean, I think that is a very interesting question. It's a concern.
But that's where we could work on, right?
Right. But what you realize here is that, what has been done when this annealing procedure is very simple in a way, right? It's
it doesn't work.
It doesn't work because what you do is you anneal in temperature, you anneal in this. It's always you're trying to find a path in distribution space, which is continuous and in a way that. But you realize here that with this type of methods, you could actually learn paths that potentially can avoid this. Okay? There's two things that you can do. What I showed here is that in principle you can get transport that have no weights. But the velocity field that are associated with it might be very bad. Right? You could imagine that that in order to do that you need to have a B that at some point does something which is dramatic. But then you can put in the objective other things that, for example, would minimize the W2 length of the path. This is also something that you can write down in terms of the B. Right? It's just the integral of B squared rho, the expectation of B squared. So then you can start to have control on different things here that would potentially allow you to pass phase transition. I can tell you one thing for sure, okay? Without data, so if you just have an oracle that gives you the potential, this remains a problem that I don't know or to solve.
What do you say?
Suppose that what you're only given is say the 5-4 model, like the energy. You have no data to begin with.
Just the U.
Just the U. Then the problem remains hard to solve from a practical standpoint. But what these methods show, okay, is that if you had sample, so it's a bit this chicken egg problem. If you had sample, you could find a velocity field that actually has very nice property. When in this framework, when you do this, right? You can actually, you have control on the W2 length in measure space that you have here, and you can show that it's finite and bounded and controlled by what you put for the interpolant. So with these models, if you give me any system that is past phase transition, and I want to push a Gaussian into it, but you will be able to pass it, and it is important because it means that the transport would go through the phase transition with no problem. So that means it's possible. Now, if you don't have the data, well, then you need to. Then it's a little bit complicated. But I believe that there is hope. That's I'm an optimist. But
so if if I can just make a comment, I mean, there's, you know, let's say in my world, there are two communities, and one of the communities is saying that the world of algorithm development, you know, time of algorithm development is over, and the only thing that where progress can come is in this trajectory from t equals to 0 to t equals to 1. And other people, to which I belong, think that we need better samplers at a given t. We have to improve on the sampling.
I'm with you on the second camp, but what I think is that this better sampler will come with learning. And I also believe, like, I sorry if I insist on this, maybe if but I do think that the status quo, there's many things that have not been solved for a long, you know, there's many problems that have been there for quite a long time. But there is really a new toolbox that has appeared, and it's not a gadget. Like, it might feel that, you know, the machine learning and these things is just a gadget, even though if it was just a gadget, it's one that has already profoundly impacted our lives, right? But I believe that it's more than that. There is something in there that really might allow to revisit calculations that we thought were completely impossible. And I you know, it's like, it's really, it's a phase transition of another kind, which is that there is something new in town, and that doesn't happen. We are lucky to have it in our lifetime, I think. Yes. I don't know.
Do you learn B in the first part? Do you learn B online or offline?
So, there's in machine learning there's this terminology which is simulation free that might mean different things. We need to simulate the SDE. Let me try to explain this. And I don't know if you, I mean, how familiar you are with, but to minimize this loss, right? Maybe I think.
Let's understand. Is it done online or offline?
It's done online, but the important part is that when you take the gradient of this objective, you can detach the data from the computational graph of the differentiation with respect to B. And that is because since this objective works for any row, the expectation and differentiation commute. So it's not completely simulation free because you need to generate the data by solving the SDE to get this XT. But the really costly part that you would have would be that if you then had to differentiate through the solution of the SDE with adjoint method, that is a killer. You don't need to do that. Okay, so I hope that answers your question.
Two quick questions. One is there many fields B, many dynamical optimal transports which push mu0 into mu1? So where is that you choose one in this formulation? How do you tell which one to learn, if I'm making sense?
In this one or in the last part?
In the first one, in the Monte Carlo one. In this one, in the nailing pot example.
So that's, I mean, this is what we are working on right now, which is, and that's related to the previous question. So far, we have prescribed the UT. Okay, the way we work is that you pick U0, you pick U1, and then, for example, you do linear interpolation. But what we are now working on is we can throw the U into the optimization by adding a criterion that will, for example, diminish the length of the curve or make that, you know, the Lipschitz constant of the B remain small. There's many things that can be.
Related to this, like you said, that when you have no data, it fails. Does it fail because this path is not a good path, or or because you need too many samples to learn B?
So there are different ways. Is that it could be difficult to actually do this optimization. The way we do it is with some form of annealing, which is that you don't, as you realize when you do that, they've integrated this in time, but you don't need to integrate from 0 to 1. What you can do is that you can take your samples and then you propagate them a little bit from 0 to delta t, or, you know, first check mark, and then you try to learn the transport there. Then if you have learned well the transport there, you don't need to relearn it, you can keep going. So there's an annealing procedure to do it. So that can be tricky, but it can be. The reason why it can fail is that you could imagine that, and that's what, you know, the phase transition, you could imagine that along the way, as the U vary continuously, but the Z, for example, the partition function can change dramatically, and so the B may have to do very dramatic things very suddenly, right? And so that's why typically we will need to improve on the path. If we were able to do the interpolation in sample space, like I did at the end, then you can avoid all of these problems, because there the length is always very well controlled.
So you say that B does something dramatic, but it's also a problem of your sample, which is that at the end you have a finite number of workers, they are somewhere, and if they don't know that they have to, if you have no observation somewhere else, where the mass starts being
that's right.
Is it the same?
Yeah. So exactly, you're right. I mean, it's totally this. Is that at the end of the day, you need to have samples. If a mode appears in your distribution, you need to have samples there to indicate. So, for example, if you had a UT, right, that is like this, and then there is a well that appears over there in a way which is completely discontinuous. All your sample, you will never discover that, right? That's this problem. That problem will never be solved, I think. Right? If there are regions that you don't know about,
samplers. It will be solved with better samplers at T.
I mean, even the optimist that I am is a pretty pessimistic on that one.
Thank you. So I wanted to ask if you can comment. If I have a problem that I want to solve, sort of this transport field that I want to find, how do I choose my neural network? Is there some trick, sort of, which neural network do I choose?
Okay, so you know, one of the advantages of this field, right, is that it has attracted so much attention, and the community is so large that there is an enormous amount of know-how, and all of the codes are public. That's actually, you know, something which is truly remarkable, which is that you're sort of forced to put. So if you want to do this, for example, for what we did for images, right? Of course, we didn't think, oh, what we will do the network. We just took the network that had been used by people in the field before. Of course, we cannot use the one that OpenAI or Google are using because they are too big for us to manipulate, but we can use baby version of the same type. So if you have a specific problem, you know, typically with a little bit of thinking, you'll know in which class it is and which type of network you should use, okay? That doesn't mean that it will not be painful or, you know, to actually adapt all the meta-parameters in there and do the optimization, but there is a lot of material available out there already.
I can add a short one. So what you said that it's very important to have samples in order to find B. What if rare events are important? So not all of your samples are kind of like
but you, okay, so I mean, these methods can be turned into, you know, method for rare events, because in a way, because what you could do here is that the way but you all know that, I mean, the way you define U0 and U1 is that, for example, you could, you know, U0 could be the distribution that you want to sample, then you want to sample the tail, the U1 would be the U1 would add a tilting factor, right? And so this would be kind of, as you typically do, is that you take your base distribution, which is the one you're interested in, you want to sample its tail, and so you tilt it toward the tail in a continuous way. But as we know, the way you do the tilting can actually matter. But you can, in principle, you know, do rare event simulation with this.
Thank you.
We need to move forward, but we have a free afternoon today, so you can grill as much as you want.
Okay.
Thank you, Eric.